Fermat's last theorem, the generalized difference of power equations, Part 2. My motto, plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. We can see from 1 and 2 that taking the binomial expansions of a plus b to the powers n and letting b equal 1 to infinity, that we generate the identical equations obtained in Part 1 and highlighted blue. In the words of Leonhard Euler, besides the same formula having been already found by methods altogether different, there can be no doubt with regard to the accuracy of the method which we have now employed. I produced the differences table shown here for my previous upload, factorials as numeric polynomials. They differ from those of Part 1 only insofar as we now keep the larger of the two powers constant and decrease the smaller power by 1 at each step. Tables also demonstrate the factorial law of finite differences, which is that the nth finite difference of adjacent integers is constant and equal to n factorial. The occurrence of a Fermat triple would violate this law. The examples in 3 and 4 show that making the binomial expansions of a minus b to the powers n and letting b equal 1 to infinity, that we generate the identical equations obtained on the previous slide, where we again keep the larger of the two powers constant and decrease the smaller power by 1 at each step. I have shown before in previous videos the following numerical sequences where, for the differences of adjacent integers raised to a power, we just substitute the power and difference of the preceding power in the workout columns 2 and 3 highlighted blue. The red differences and the fourth power substituted in columns 2 and 3 will give the differences of the fifth power. Starting with just the difference of squares in 1, I end up with the same numeric sequence as the previous slide, from which I obtained the difference of the cubes. In 2, I have taken the difference of the quartics and applied the difference of squares twice, which after numeric consolidation and rearrangement as per the squares allows the difference of the quintics to be specified. Note that this method only works for the exponent equal to 2 to the power n. To qualify what we have just done, the 10 minus 9 equals 1 highlighted red is there because what we are actually calculating is x to the power n minus y to the power n all divided by x minus y, and therefore allows the difference of powers of non-adjacent integers to be evaluated as the following shows in 3, where from 10 squared minus 7 squared we end up with 10 cubed minus 7 cubed. There is no suggestion in what I have done or what follows that the equations or methods shown are the best way of calculating differences of powers, when all one needs is a to the n minus b to the n. It is purely to demonstrate the algebraic and numeric uniformity, regularity and interconnectivity of the differences of powers, so that the chaos that would result due to a Fermat triple is evident even to us mere mortals. Intuitive equations for the difference of powers. I have covered this item before, but have included it here for completeness. Orange rectangle a to the power n equals a times a to the power n minus 1. Black rectangle b to the power n equals b times b to the power n minus 1. Therefore, a to the power n minus b to the power n is equal to a times a to the power n minus 1 minus b times b to the power n minus 1. We can intuitively deduce equations 1 and equations 2, which I have confirmed numerically. And after a rearrangement, we have equations 1a and 2a. As far as I am concerned, equations 1 and 2 are equations of ascent to infinity, after which rearrangement becomes equations of descent from infinity, albeit to the limit a to the 0, at which level of exponentiation all differences are 0. My gut feeling is that this was Pierre de Fermat's concept of infinite descent, and not the modern interpretation of a never-ending recursion. The difference of cubes and triangular numbers. In 1, I have demonstrated how from the difference of squares for an integer we can generate a difference of squares for a cube, the roots of the squares being adjacent triangular numbers for adjacent integers. It is thus possible to state the difference of cubes as the sum of two squares minus the sum of two squares. The same can be repeated for the fifth and all subsequent odd powers. As the powers increase, we get ever more difference of square solutions, so the permutations get bigger and bigger for any one difference of powers. This can make an absurdity of the notion of a Fermat triple. We can continue this argument for each and every odd power all the way to infinity. This is a copy of the table of slide 5, but just for the cubes, but with the extremely important statement added as a footer to the table, which says, the difference of the cubes for every pair of adjacent integers is equal to 6 times a triangular number plus 1, where the rank of the triangular number is equal to the root of the smaller of the two cubes. Everything we have done in parts 1 and 2 has demonstrated the interconnectivity of the powers and their differences. Hence, the triangular numbers being a divergent sequence and intimately connected with the difference of cubes imposes this divergence in ever increasing degree on higher powers, noting that many higher powers are squares, cubes, etc. of the cubes themselves. So as the algebra being applicable to all powers shows, what was not possible for the cubes regarding the Fermat triple was certainly not possible for higher powers. So a proof for the cubes was indeed a proof for all. So the quest for the modern proof was indeed nothing but a fool's errand.